Welcome to this particular class. This would be a series of modules that you need to go through, and the idea is to explain the importance of micro machining. Now, when we talk about MEMS, what exactly MEMS are? MEMS are micro electro mechanical systems, right. So, electronics, when we design electronics using micro technology, we can understand what is a mechanical, right. Micro electromechanical, where is mechanical things comes into picture. So, if you know, right, we perform machining in a mechanical workshop, right. We have seen we use lathe machine, we use other drilling machine, and we perform machining, right. So, you take a material, you etch the material, right. You can form something similar to etching of this particular material, right. So, you can we can create this machining in a bigger surface, in a bigger area. What about you want to perform machining in a smaller dimension, in a micro dimension? That will be your micro machining, right. Machining at a micron scale, micro machining. So, let us learn and let us see why this machining knowledge is very important for us to understand and how we can use it to fabricate some sensors, right. So, when you talk about machining, there are two types of machining. One is bulk machining and second is surface machining. So, bulk micro machining, surface micro machining. So, let us see what exactly bulk micro machining is, and then we will see what is surface micro machining, and then bulk plus surface micro machining, and we will take few examples, right. So, let us see what is micro machining. Micro machining. Micro machining is derived from a traditional machining process, like I said, such as turning, milling, laser machining, etc., by judicious modification of these machines, correct. Then micro machining is the basic technology for fabrication of micro components. Micro, what does micro means? 10 raised to or 10 to the power minus 6 of a meter, micrometer, right. Components of size in the range of 10 to the power minus 6 meters. Materials on a micrometer scale possesses unique properties. Micro machining process is used to fabricate MEMS based devices, integrated circuits, etc. Also, micro machining is a parallel, that is batch process, in which dozens to tens of thousands of identical elements are fabricated simultaneously on the same wafer, right. So, if you see machining technology, then you will understand that we can have a batch processing where thousands of identical elements can be fabricated on a single wafer at one time, that is simultaneously. So, now let us further see bulk and surface micro machining, right. Bulk and surface micro machining. Bulk micro machining is a process that produces structure inside the substrate by selective etching. You see, he is only etching this part, right, he is only breaking this part, these parts are intact, remaining parts are intact. So, selectively breaking something or etching something, right, within a substrate we can define as a bulk micro machining, right. We will see a better example. While in case of a surface micro machining, this is a process that creates structure on the top of the substrate by film deposition and selective etching, right. We can deposit a film and selectively etch the film. So, there is a fundamental difference, as we can see, between bulk micro machining and surface micro machining technologies. So, let us understand very important definitions on etching. you can say parameters, you can say properties, right. What are these properties? First property is aspect ratio. What is aspect ratio? Ratio of height to lateral dimensions of the H microstructure. You can see here, right, height to lateral dimension is a aspect ratio, okay, ratio of height to lateral dimension of etched microstructures. Second is selectivity. What is selectivity? Selectivity is the ability of the process to choose between the layer to be removed and interleaving layers. So, if you see in this particular case, right, if you see this example, right, in this example what we are doing? We are selectively etching only this surface, you can see here, right, it is etched, this green section is etched without affecting any black section, without affecting the black section, we are selectively etching this area. This is the selectivity, okay. Next, what is next? Next is etch rate. Etch rate is the speed with which the process progresses. Suppose I have a silicon dioxide, let me just draw it once again, okay. I have a oxidized silicon wafer. What is oxidized silicon wafer? Silicon dioxide, right. Now, using photolithography, I have created a window and etch silicon dioxide, right. Now, I want to etch silicon. So, how fast I can etch silicon is my etch rate, right. So, I have we know that for etching silicon using wet etching, chemical etching, we have potassium hydroxide and we have TMAH, right. And if you remember, potassium hydroxide we perform etching at 80 degree centigrade, TMAH at 25 degree centigrade, KOH is faster etching, TMAH is slower etching, KOH the surface roughness is poor, right, surface roughness is poor, TMAH surface roughness is smoother, so better, right. This is coarser, this is smoother, this is smooth, this is rough, right. Advantages, disadvantages. Now, one thing that we have seen is the etch rate for KOH is higher, that means the silicon can be etched faster, that is what etch rate means, that is what etch rate means, right. Now, when I am dipping this wafer in KOH or TMAH, only silicon will get etched and silicon dioxide will not get affected, silicon dioxide will not get affected. So, silicon dioxide is not getting affected and only silicon is getting etched, that is our selectivity, right. So, just quickly wanted to show you an example. Now, next would be etch profile. What is etch profile? Slope of the etched well, slope of the etch well, and it is nothing but etch rate 1 by etch rate 2. Also, anisotropy. What is anisotropy? Anisotropy is 1 minus R lateral divided by R vertical, rate of lateral etching divided by rate of vertical etching, right. So, these are some of the definitions when we are talking about etching, right. Etching, like I said, very important, and you can create several structures using bulk micromachining and surface micromachining. So, let us see what kind of structures we can design or we can fabricate using surface micromachining. So, you can see here, this is an example of surface micromachining, and if you see this example, the gray color is silicon and black color is oxide. So, if you see the side view, right, we have oxide on silicon. Now, we are depositing a metal we are depositing a metal and then we are etching oxide, we are etching oxide. What will happen? We will have a cantilever, right. We will have cantilever of what? We will have cantilever of metal, right. So, this is how we can create a cantilever. Now, carving of layers put down sequentially on the substrate by using selective etching of sacrificial thin films to form freestanding completely released thin film microstructures. That is what surface micromachining does, right. What it does? Carving of layers put down sequentially on substrate. You see here we have silicon dioxide on silicon, we deposited a metal, right, and then we have etched the silicon dioxide. So, silicon dioxide here would be a sacrificial layer, it will sacrifice itself, sacrificial layer. So, when I sacrifice silicon dioxide by etching silicon dioxide in buffer hydrofluoric acid, what I will have? I will have a cantilever made up of a metal. Next is, it is difficult to release as surface tension forces are greater than gravitational forces at micro scale. So, at micro scale you should understand that the gravitational forces are less compared to surface tension forces, and that is why it is difficult to release cantilevers. Now, you can see here there is a nickel iron cantilever fabricated using surface micromachining process, and you can see multiple cantilevers the author has tried to fabricate, right. Some are really beautiful. You can see here it is a perfect example of how cantilever can be released. Some have the curvature, right, some are not released. So, you can see here the cantilevers which are released are these cantilevers, but they are buckled up, right. This cantilever in particular is not released because otherwise it will come up. So, this cantilever is not released, this one is released, again buckled up, right. Same way this cantilever is not released, right. So, it is difficult to release the cantilever, like I said, because surface tension forces are greater than gravitational forces. However, if you see that there are few cantilevers that were destroyed during the fabrication process, few cantilevers that got buckled up because of the stress in the metal film, right. However, you can get if you optimize the parameter, you can get excellently released cantilevers, right. I will show you an example of how to release a cantilever, but using a bulk micromachining process in the following slides. The point is, using surface micromachining we can easily fabricate a structure, but then we need to optimize the parameter, otherwise because of the surface tension being higher or greater than gravitational force, it is very difficult to release the structure in a proper fashion, right. So, when you see now, if you go back to the slide, what you will see, there is a bulk silicon micromachining, right, bulk silicon micromachining. So, in bulk silicon micromachining we will see two kind of etching, one is wet etching and another one is dry etching, alright. One is wet etching, another one is dry etching. Now, in wet etching there is isotropic etching and anisotropic etching. Similarly, in dry etching there is isotropic etching and there is anisotropic etching. Now, dry etching anisotropic property depends on the process, while in case of wet etching the anisotropic is dependent on crystal orientation. Now, if it is acidic etchants, then we will generally get isotropic, while if it is alkaline we will get anisotropic. In the case of F based plasma we will get anisotropic, while this is the case of dry etching, while we have BRF3 or XCF2 will get isotropic etching. So, DRI is a deep reactive ion etching, is a example of dry etching, and dry etching is also commonly known as plasma etching, because we are generating a plasma and the electron energy in the plasma creates a very high temperature, but the overall process it is at low temperature. So, the gases will etch the silicon, and for silicon we use generally C4, F8 and SF6, while we also use helium and oxygen in case of the deep reactive ion etching. We will see a video of how deep reactive ion etcher can be used from STS. So, the one of the big problem in the isotropic in the etching world is the undercut problem, right. So, you can see here isotropic etching and anisotropic etching. So, if this is the window, we want to etch this window, then etch rate is agitation and temperature sensitive. So, here it will be temperature sensitive and depending on the chemical, difficult to control lateral and vertical etch rates, right. This and this very difficult to control, lateral and vertical etch rates very difficult to control. While in the case of anisotropic etching, etch rate is temperature sensitive, but self limited by its orientation, and of course, it is orientation dependent, it is orientation dependent. So, this is about the isotropic and anisotropic etching. Okay. Now, when we are talking about isotropic and anisotropic etching, let us talk about wet anisotropic etching. Wet anisotropic etching. Okay. So, you can see here that anisotropically etched cavity in 100 silicon with a square mask film opening oriented parallel to the 100 direction, right. So, when we want to etch, we have to take this, the etch rate is defined in this particular fashion, where the 110 is to 100 is to 111. As you can see, 111 will not get etched compared to 100 and 110, right. So, the cavity defined walls are 111 walls slow etching planes, while 100 which is floor, right, this one is slow etching plane, while the floor which is 100 is a fast etching plane. The floor is faster, the cavity walls would be slow because of the 111 crystal orientation. If you want to see this is what is the final depth that you are etching, right, that you want to see, then you need to calculate what is the final depth that you want, and depending on that you have to open the window which is WO. So, if I say the opening of the window is WO, the final depth this one, this width, right, this one, this will be my WB, initial window that I have to open is WO. How is related? So, WB equals to WO minus 2 into I into cot theta, where cot theta is nothing but 54.7 degree. So, when you want to etch it, right, the etching is done, wet etching is done, wet etching of silicon, it creates an angle of 54.7 degree. Now, you can I said I, but you can say L or I, it is a length, it is a length. Of course, the silicon dioxide will act as a mask. So, when you dip this wafer in KOH or TMAH, the silicon below silicon dioxide will not get etched, as you can see here or here, right. And if it is a 111 wall creating plane, then you can see that it is slow, while if it is 100 creating plane, it is faster. So, the opening of the window, if I want a particular depth with a particular lateral etching, I need to know what is the initial opening of the window that I have to create. For example, if I have oxidized silicon wafer, if I create a window which is my WO, right, what will be my final etching WB? this WB can be calculated using this formula, right. What is the depth that I want to etch, right, what is the initial window that I will have, and if I know the angle, then I can create, which is angle is 54.7 degree, I can create my WO accordingly, so that I can achieve my WB of a particular dimension, right. Now, the final shape of the cavity also depends on geometry of the mask and etching time. Okay. So, etching time and geometry of the mask are the another two factors that decides the final shape of the cavity. Also, the shape of the cavity can be V grooved, like a V groove, it can be a pyramid, right, or it can be a truncated pyramid. So, these three are the patterns that you can obtain when you are etching a silicon wafer, V groove, pyramid or a truncated pyramid. So, if you see the example here, you can see, right, V groove, pyramid or truncated pyramid, and these are cantilevers which are released. You can see here a completely released cantilever, right, and of course, this is taken from Microsystem Technologies, written by Prempal ETL. This is just a schematic diagram. Also, there is another paper that we have used from Jory ETL to get the idea of how the cantilever looks like when it is released with the help of the etching technology, right. So, like I said, we can have V groove, we can have truncated pyramid, and we can have pyramid, three types of structure when we are using micro machining. So, until now what we have seen? We have seen that the micro machining can be two types, one is bulk micro machining, one is surface micro machining. And then we have seen how the bulk micro machining and surface micro machining can be used with an example of releasing a cantilever using surface micro machining. Now, we will see an examples that is will be I will show you the examples in the next module of how to create volatile organic compounds based sensors using bulk micro machining and using bulk plus surface micro machining. Right. Till then, you just go through this module. I will see you in the next module to discuss more about how to use micro machining technologies to create a device. Yeah. Till then, take care. I will see you in next class.